In this video, we will take a look at navigation and velocity vectors. We'll begin by talking about velocity vectors. Velocity vectors are vectors that represent the speed and the direction of an object. So, for example, using the equation that we saw in a previous video, where the vector is equal to x times unit vector I plus y times unit vector j, we were able to say that that is equal to the magnitude of the vector times the cosine of theta times unit vector I plus, again, the magnitude of the vector v times the sine of theta times unit vector j. Another way to write that is by recognizing that in both of those terms there was a magnitude of vector v. So I'm going to factor that out and say that we can now just write the magnitude of the vector times the quantity cosine of theta I plus sine of theta j. And we can use that to help us describe what this vector might represent. This vector says 24.3 times the quantity of the cosine of 30 degrees I plus the sine of 30 degrees j. So this very first number, the 24.3, that represents the magnitude of the vector. So we might say that this represents an object, some object, that is traveling at a magnitude or a speed, we might say, of 24.3, and no units are given, so maybe I'll just say miles per hour, question mark. So we want to pay attention to that in any word problems we're given. Usually the units are given. And a direction of, the direction is the theta, and that theta is from the positive x-axis or from the x-axis. So we would say at a direction of 30 degrees from the positive horizontal axis. Horizontal axis is better to say than x-axis because we don't always know that it is the x-axis. It could be labeled something else. Now, another way to say that would be as a bearing. Okay, and bearings are measured from north and south. So if I just draw a little sketch of what's going on here, north faces up, south faces down, west points to the left, and east points to the right. If this object is traveling 30 degrees from the positive horizontal axis, then we know that the bearing, which is starting from the north in this case, would be 60 degrees because 60 degrees plus 30 degrees makes up that first quadrant. So we would say as a bearing of north 60 degrees east. Now notice if a problem is given information like that with a bearing, don't automatically put the number that you see there, the 60 degrees, in for your theta because this theta is measured from the positive horizontal axis. So something to be careful of. Let's try looking at an example. In this example, we're being asked to find the speed and direction using just components. So we have an airplane that's headed north at an airspeed of 600 kilometers per hour. Then we have some wind that's blowing from the southwest at 80 kilometers per hour. They want us to do two things on this first part. Express the velocity vector of the airspeed, we're going to call that v sub a, and the velocity vector of the wind speed, which we're going to call v sub w, just to keep those separate. Okay, so let's first talk about the airplane. All right, what is the airplane doing? The airplane is, just going to draw myself a little compass here. So we have north, we have south, we have west, and we have east. Very convenient that that also is a coordinate plane, isn't it? So this airplane is headed north, and they're headed north at a speed of 600 kilometers per hour. So we're going to say that v sub a is equal to that speed of 600 times the cosine of the angle measure from the positive x-axis, which is 90 degrees I, so 90 degrees, and then plus the sine of 90 degrees j. Okay, and I'm going to actually calculate that out. Let's see, what is the cosine of 90 degrees? The cosine of 90 degrees is 0, and the sine of 90 degrees is 1. So 0 times anything is just 0, so that one goes away, and we're left with simply 600j. Okay, so remember, unit vector I represents horizontal movement, unit vector j represents vertical movement. So starting at the origin, this vector is simply involving a vertical movement of 600 units. Okay, now let's talk about the wind. What is the wind doing? The wind, and let me see if I can just sort of squeeze this in here. The wind is headed from, what did it say? It's headed from the southwest. So here's the south pointing down, and the west is to the left. So if the wind is blowing from the southwest, then it is leading us in the direction of the first quadrant. That's where it's blowing from. And when they don't give you an actual angle measure and they use something like southwest, you can assume that it's cutting that quadrant right in half. So that means that the angle from the positive x-axis is 45 degrees. And of course we know, because it's been given, that the length of that vector is going to be 80. So I'm going to say that vector v sub w is equal to, actually let me erase this and put it up one, because I'm going to want to actually calculate what that is, and I'll use black to distinguish it. So I'm going to say vector v sub w is equal to 80 times the cosine of 45 degrees I plus the sine of 45 degrees j. Now, if you're ever given an angle measure that you don't have memorized what the value is, then it might be appropriate to use a calculator. In this particular case, I think we can say what those are equal to. Both the sine and the cosine of 45 degrees is the square root of 2 over 2. So this is going to be 80 times the square root of 2 over 2i plus the square root of 2 over 2j. And if I distribute that 80 through, I get 40 root 2i plus 40 root 2j. Sorry, that was so small, but I think I was able to squeeze it in there. I'm going to show this on the next slide, and I'll give it a little bit more space. All right, so let's keep this example going. This is where we ended up. I went ahead and wrote these a little bit nicer. We have that the airspeed vector is 600j, so that was the vector or the airplane headed north. And then we have the wind speed vector that was 40 root 2i plus 40 root 2j. Now, if you were to want to sort of wrap your head around what that wind speed vector represents, you could put 40 times the square root of 2 into your calculator, and you would get that this is equal to 40 times the square root of 2 is around 56.6 I. So it would be that number again, j. And what that represents is a position vector. So, we started with the wind headed from the southwest, right? So what this 56.6 is saying is that if I start at the origin and I go 56.6 units to the right and 56.6 units up, that I'm going to run into that vector. That's what that represents. Okay, let's take a look at part B. Part B says to express the velocity vector of the ground speed. Okay, we saw airspeed, we saw wind speed. to find the velocity vector of the ground speed, where airspeed plus wind speed is equal to ground speed. Maybe let me get rid of this little picture so you can actually see what this says. Okay, so they want us to find ground speed. So V sub G is going to equal whatever V sub A was, V sub A, which is 600, J, plus whatever the wind speed vector was. So the wind speed vector we found to be 40 root 2 I plus 40 root 2 J. And I'm going to simplify that one more time, and I'm going to combine like unit vectors. So I get 40 root 2 I plus 600, the quantity of 600 plus 40 root 2 J. Okay, so I took the two J terms and I combined them into one. All right, so there's where I'm at. Let's go to part C now. Part C says to find the airplane's actual speed relative to the ground. So the idea here is that the plane started out going north, but then there's this wind that's coming from the southwest, and that wind is headed into the first quadrant. It's blowing that plane off course. It's not only blowing it off course, but it might be speeding it up or it might be slowing it down. To find out if it's speeding it up or slowing it down, then what we need to do is to find out or to calculate what the actual speed is. And the actual speed is given as the magnitude of that ground speed vector. So what I want to find out is what that is. Now, do you remember how to find magnitude? So the way that you find magnitude is the square root of, I'm going to take my I term, which was, where's the I term? Here it was up here. It was the 400 times the square root of 2. So I'm going to take 40 times the square root of 2. I'm going to square that, plus, then I'm going to take my J term, and I'm going to square that. Now, again, I could be using a calculator to come up with decimal approximations, but if you can leave it in exact form until the very end, you'll save yourself some problems with rounding. So I want you to pause the video and put this into your calculator. Be very careful. The square root of 40 root 2 squared plus the quantity of 600 plus 40 root 2 also squared. And when I put that into my calculator, I got approximately, and they say to round to the nearest whole kilometer per hour, I got approximately 659 kilometers per hour. Now remember, the plane started at 600 kilometers per hour, and it looks like that wind sped it up just a little bit, didn't it? And that feels believable. Usually I expect a number that's within plus or minus that area. Okay, the last thing to figure out is what has happened to the plane's direction? What has happened to the plane's direction? And we want to write that as a bearing. Okay, so as a bearing, let's see here. To find the angle, first we're going to just find what theta is. And the way that you find theta is you take tangent of theta, and that is going to equal it's going to be my y over my x value, but in this example, my y value is this 600 plus 40 root 2. So I'm going to put 600 plus 40 root 2 all over my x value, which was the I piece. So 40 times the square root of 2. And what I'm actually going to put into my calculator is I'm going to take inverse tangent of each side. I'm going to put that into my calculator. All of those exact numbers. And they say to round to the nearest tenth of a degree. Now, when I did that, I got a theta of approximately 85.1 degrees. And I think that that feels believable as well. If you remember, let's just see here. So I started out going north, right? Started out going north. And then there was this wind. There's the wind. And it blew me off course, didn't it? It blew me off course and it put me in a new position. So no longer am I 45 degrees from the horizontal. I am now, what am I? 85 degrees from the horizontal? 85 degrees from the horizontal. So I was going north. The wind has blown me off course. This is now what I'm doing. It says to write it as a bearing. Is that 85.1 degree a bearing? And the answer is no. The bearing is always from the north or the south. So what is this angle that is between the actual vector for the actual speed and the north direction? Well, we know that whole angle in the first quadrant is 90 degrees, and we know from the positive horizontal axis we have 85.1 degrees. So I'm going to say that the new direction of this plane is that it's headed north. It's being thrown off course toward the east, right? Here is the east. And that bearing is whatever 90 degrees minus the 85.1 degrees that we found was. And if I use my calculator for that, I get 4.9 degrees. So that is the effect of the wind on this airspeed vector. In the last example, we solved this example using components. In this example, we're going to try solving the exact same thing, but now using law of sine and cosine. So here was the problem that we just solved a second ago. An airplane is headed north at an airspeed of 600 kilometers per hour, and we know that we have a wind blowing from the southwest at 800 kilometers per hour. Find the airplane's actual speed relative to the ground, rounded to the nearest whole kilometer per hour, and then find the airplane's actual direction, written as a bearing, rounded to the nearest tenth of a degree. And we see on this page that we have an XY axis, which can also represent our compass, our north, south, west, and east. And the way that we're going to do this one is by using vector addition. Now we did vector addition with the components. We had the I components and the J components, and we combined like terms. What I mean here is we're going to actually draw the vectors in, and we're going to do vector addition by connecting terminal points to initial points. Let me show you what I mean. I'm going to start with the airplane headed north at an airspeed of 600 kilometers per hour. So this red vector is my airspeed vector, and I am traveling at 600 kilometers per hour. So that is my airspeed vector. Then we have the wind, right, coming from the southwest. And we saw in that example that it was coming from the southwest, right, and it ended up going into the first quadrant. What I'm going to do is I'm going to pick that vector up, and I'm going to connect its initial point to the terminal point of the airspeed vector. So it's going to look something like this. It's going to look coming off of that terminal point of the airspeed vector. Now, one thing that sometimes can help is when you are connecting vectors to just make yourself another little XY axis here, because we know that that wind speed vector created a 45-degree angle with its horizontal. We still have that 45 degree with the horizontal. We just now also happen to have a 90-degree right angle. So we know what this whole angle measure is, or at least we can calculate it. 90 degrees plus 45 degrees is 135 degrees. Okay, we'll figure out why we need that in just a second. So let me label here, the length of this vector is 80. Definitely not drawn to scale, right? That vector should be much smaller than the airspeed vector of 600, but I've labeled it so you get the idea. And I'm going to label this as my wind speed. Now, when we did the component addition, we said that ground speed is equal to airspeed plus wind speed. Well, that's what we have here. We have the airspeed vector plus the wind speed vector. And if I close off this triangle, then what I have just created is what I'm looking for, which is ground speed. So I just need to find the length of the side of that triangle. And I can do that using, let's see, law of sine or cosine. I'm being given a side, I know an angle, and then I know another side, don't I? So I have side angle side, and when you have side angle side, you can use the law of cosines to solve. Now, the side that I'm trying to determine is, I'll call it x, okay? Let's call that x. So using the law of cosines, I can say that x to the second power is equal to 600 squared plus 80 squared minus 2 times 600 times 80 times the cosine of the angle that's across from x. And the angle that's across from x, you sort of lost that 1 right there, is 135 degrees. Now, I'm going to put all of this into my calculator, and then to find out what x actually equals, I'm going to square root it. So when I did that, and you should pause the video and make sure it works, I got the same answer of 659 kilometers per hour that I saw on the last slide using the component method of adding vectors. Okay, so you might think, wow, this was a lot easier, and I would agree that there is less computation. What this method hinges on is whether or not you can draw this picture and connect terminal points to initial points and then recognize the piece that's left over for you to solve for. Now, the last piece of this is to find the airplane's actual direction. So the airplane is actually flying now in this direction. So there is an angle with the horizontal axis. There's an angle with the vertical axis. Which one is the bearing? Well, the answer to that is the angle with the vertical axis, the angle that is positioned next to north. I'm going to call that theta. So if I can solve for that theta, then I have found the bearing. So should I use law of sine or cosine? I could probably use either. Most of the time, I think in books, you're going to see them use law of sines. People tend to like that better. And the reason I can use law of sines is because I'm trying to find theta, and I do know the side across from it. That's that length of 80. And then, of course, I also have an anchor now because I have solved for x. So here's what I'm going to write. I'm going to say that the sine of theta, that unknown angle, over the side across from it, which is 80, is equal to, I'm going to use my anchor now, I'm going to say the sine of the 135 degree angle all over x, and x was 659 with some change, right? When I actually put this into my calculator, I'm going to put into my calculator whatever that full value of x was. And I don't have that right in front of me right now, but hopefully you've got it on your calculator. That's what you're going to use. You're not going to use the rounded version of 659 because if you do, it could cause a little bit of a computation error. Okay, I'm going to multiply both sides by 80, and that is going to clear. Let me go ahead and do that. Multiply both sides by 80. So I'm going to multiply both sides by 80. The 80s cancel out, and I'm left with the sine of theta is equal to 80 times the sine of 135 degrees all over 659. So in order to get this thing by itself, the theta by itself, I need to take inverse sine of both sides. So I'm going to get sine inverse of the sine of 135 degrees times 80 all over 659. And when you put all of that into your calculator, what you should have gotten rounded is 4.9 degrees. And that 4.9 degrees, is headed north and then traveling a little bit to the east. And that answer also matches. So we now have two ways of doing these navigation problems. We can do it this way using law of sine or cosine, where we're simply connecting terminal sides to initial sides and creating a triangle. Or we can do it the previous way that we just did it, using components, where the components are the unit vector I and the unit vector j. Now let's try another example. In this example, we have an airplane that is headed north 30 degrees west at an airspeed of 500 miles per hour. The wind is blowing due east at 40 miles per hour. Find the airplane's actual speed relative to the ground, rounded to the nearest whole mile per hour. Find the airplane's actual direction, written as a bearing, rounded to the nearest tenth of a degree. Okay, so we have two methods that we can do this. We can use vector component addition. That's where you have unit vector I and unit vector j. Or we could draw in the vectors and use the law of sine or cosine. I'm going to pick the component way to find the answer here. And I would challenge you, after you're done watching this, to try the law of sine and cosine and see if you can come up with the same answer. Okay, so let's see what we've got. I've got the airspeed that is going north 30 degrees west at an airspeed of 500 miles per hour. So I'm going to call this V sub A. And that is going to equal my speed, which is 500, times the cosine of. Now I got to figure out what is that angle measure with the positive x-axis. Well, if I'm headed north, but then 30 degrees toward the west, my vector looks something like this, off into the second quadrant. So the angle that that vector makes with the positive x-axis is not 30 degrees, is it? It's actually going to be 30 degrees plus 90 degrees, which is 120 degrees. That's what I'm going to use for the first piece of my vector. So cosine of 120 degrees I plus the sine of 120 degrees j. And I'll close that off. Now, 120 degrees is an angle measure that I do know its value. The cosine of 120 degrees is negative 1/2 I. And the sine of 120 degrees is the square root of 3 over 2j. And if I distribute that 500 through, I get negative 250I plus 250 times the square root of 3j. That is just me distributing this 500 through. Okay, so here's what that's saying. That's saying that this plane, if I start at the origin, that the position vector that represents this vector is me going to the left or toward the west 250 units, and then going up 250 square root of 3 units. That's how I get to that vector. Okay, second piece is the wind. The wind is blowing due east. Okay, so my wind speed vector is 40 times the cosine of, so if I'm headed, or if the wind is blowing toward the east, right? The wind is blowing toward the east, then it is literally on that positive x-axis. So I'm talking about an angle measure of 0 degrees. So cosine of 0 degrees I plus the sine of 0 degrees j. And the cosine of 0 degrees is 1, and the sine of 0 degrees is 0. So that 0, of course, cancels out, and I'm left with 40I. Okay, the next part wants me to find the airplane's actual direction. So I need a vector for find the airplane's actual speed relative to the ground. So I'm looking for v sub g, and that's going to equal the airspeed vector plus the wind speed vector. Okay, and I can write something down for that. I'm going to take the airspeed vector and the wind speed vector, and I'm going to collect what I call like terms. So I've got negative, oops, I used my eraser instead of the highlighter. Let me just write that on there again. So that was negative 250, wasn't it? So I'm going to take negative 250 and 40. Those are both i's, and I'm going to add those. So what is negative 250 plus 40? That gives me negative 210i plus, the only thing that's left for j is 250 root 3. So I'm going to call that 250 root 3. There's nothing to add that to. Okay, so that is my ground speed vector. Now, what do I do with that ground speed vector? Well, I want to find the actual speed. So to find the actual speed, I'm going to take the magnitude of, that ground speed vector, which means I'm going to take the square root of, I'm going to put negative 210 and square it. I'm going to take 250 root 3 and square it. And I'm going to add those two. And then I'm going to take the square root. And whatever answer I get, I'm going to round to the nearest whole mile per hour. And when I did this, I got 480, I got 481.2 miles per hour. So rounded to the nearest whole mile per hour, that would be 481 miles per hour. Remember, I started at a speed of 500, right? 500, and then I had the wind, right, that was blowing toward the east. So the wind in this case was really sort of throwing me off course, wasn't it? And because it was throwing me off course, it was slowing me down. Now, how far off course was it throwing me off? Well, now we have to bring the tangent into this. So I'm going to say tangent theta is equal to my y value, which is my j component, so 250 times the square root of 3 all over the I component, which is negative 210. Now I'm going to put into my calculator tangent inverse of that amount, and when I put that into my calculator, I got negative 64.1 degrees. Now, we need to think about this, don't we? Where's negative 64.1 degrees? Negative 64.1 degrees is down in the fourth quadrant. Do we actually think that it blew it off that much? And I hope you're screaming, no, that can't be right. Well, you're right. And what you need to remember is when you put tangent inverse into your calculator, remember the calculator is only giving you one possible answer within the boundary, but there are other answers, and that is because of the period of the tangent function. If I add 180 degrees to this, I get 115.9 degrees. Now remember, what I had was 120 degrees, right? That's what the angle measure was from the positive x-axis. Now I have 115.9 degrees. That, in my opinion, is believable, right? That's about right there. But is that the bearing? And the answer is no, that is not the bearing. The bearing, let's see if I can just get this vector. I'm going to put it in green. I don't know if that's going to make it worse, but here is the new location of this vector. The bearing is the angle between that vector and either the north or the south. In this case, it's the north. So we know that that whole angle measure in that second quadrant is 90 degrees. So how do I figure out what that angle measure is right there? I think if I take 115 degrees and I subtract out the 90 degrees that is this first quadrant, right? That should give it to me, right? If this whole thing here is 115.9 degrees, then if I subtract out 90, that's going to leave me just with the bearing. So I'm going to say as my final answer that this plane is headed to the north, and then it's going west, and the direction that it's going is 115.9 degrees minus 90 degrees. And if you put that into your calculator, this whole thing becomes 25.9 degrees. Okay, so this is getting a little messy, and this method sort of does, but I think if you just pause it and rewatch this, I hope it makes sense. Remember, your challenge is to do the same exact problem, but now you try it with law of sine or cosine.